Good afternoon. Welcome to course of Thermodynamics of Materials. Today we are into lecture 141 and 42. We'll work with problem 5. We started with problem 5. Today we'll continue with problem 5. And okay, just we went halfway. Here we went up to this point. Okay, this is the problem 5, solution of problem 5. So this we are discussing. We actually went up to this. Let us not waste time. So if this is what is the equilibrium constant? Is expression for equilibrium constant. Let us write down for this is what? PCO, as you know, PCO, HC, weight percent, times HO, weight percent. Now PCO is okay, the problem said something here. Okay. Now typically PCO is, as you know, PCO is 1 atmosphere. So if this is so, then you actually have this or HC weight percent times HO weight percent is 1 over 451, which is 0.0022. 0.0022. Now, so you can box this. This is a standard expression. Remember this, you can always write, okay, enclose under equilibrium. So these are also equilibrium relation. This is a standard equilibrium relation. So this now writing HI rather, instead of writing HI is HI weight percent, as you know, approximately equals to weight percent I. If we are entitled to write this without making much error, then this approximation actually approximation holds good. Then okay, without much error, then we have this relation or weight percent carbon times weight percent oxygen is 0.0022. This is a, remember this is a standard and popular, very popular for quick calculations, popular equilibrium relation between weight percent carbon and weight percent oxygen in liquid steel at under PCO is 1 atmosphere. As we often consider exit, the gas exits at 1 atmosphere. Open to atmosphere means total pressure is 1 atmosphere, and PCO is the dominant gas, product gas CO. So PCO is 1 atmosphere at, careful about the temperature as well, 1873 Kelvin, the standard Steelmaking temperature. So this is very useful. What does it mean? If you know weight percent carbon, in liquid steel at tap, say, when it is tapped and under equilibrium it is tapped, say, equilibrium condition prevails in the steel making system, then if you know weight percent carbon, you know weight percent oxygen, how much oxygen also, very useful, very useful. Or conversely, if you know 8% oxygen, you know 8% carbon. So you know one, you know the others. That is very useful because they strike equilibrium with this. This equilibrium prevails in the steel making system. Carbon and oxygen in the liquid steel and gas, exit gas, which is CO, essentially. We strike equilibrium between metal phase and gas phase. Okay. So this is very, we sometimes will actually use this relation in solving problem. So given all this, now let us move. Okay, so what is your, now apply this thing. What is the carbon percentage at tap when it is blown to, the steel is blown with oxygen to 0.06% carbon. So given 8% carbon, what is the, so okay, 8% carbon. So when blowing is over and at equilibrium, okay, this is 0.06% carbon, 0.06 carbon, 0.06%. Hence, okay, hence 8% oxygen is what? How much? Is 0.0022 over 0.06 is how much? It's roughly 0.04, is actually 0.037%. So this is when blowing is over and before tapping, but subsequently something else is done. The steel is to deoxidize. So this is the equilibrium value in the first case, means that is the initial oxygen. Now you want to reduce this oxygen content further by adding what? By silicon, adding silicon. Silicon is a good deoxidizer, you know, is a deoxidizer. So it will remove oxygen, react with oxygen, forming silica, SiO2. Okay. So the deoxidation product is silica, solid silica, because solid silica melting point is 1723 degrees centigrade, which is above 1600 degrees centigrade. So it will be solid. So that's why this product is silica, SiO2 solid. So what is asked here, how many kg of silicon needs to be added for this deoxidation purpose? So these are two things you have to be careful. One is, what is the silicon that remains after deoxidation? It removes oxygen, but something at equilibrium, what happens? Some amount is held back, some concentration is held back, that is the equilibrium concentration. So that equilibrium silicon concentration or residual silicon concentration you have to find out from the pertinent equilibrium. That is, silicon plus oxygen goes to silica, SiO2. That is one task. Another task is what? How much oxygen is removed, and accordingly stoichiometric wise, how much silicon is removed in the form of SiO2. So silicon is removed and some silicon is retained. These together you have to find out, this total you have to find out, that you should input, that you should feed as deoxidizer, so that both the jobs are taken care of, both the jobs are fulfilled. One is are satisfied. What is this? Two jobs. One is silicon will be removed as silica, SiO2, removing oxygen. So silicon, for that purpose, silicon should be given into the system. And another is, silicon will, some of the silicon that you add will not be fully converted into silica, some will be held back. That is retained. That is the residual, that is the equilibrium. So let us calculate this. So this is this I say. Hence once more I write hence Okay. So this this hence actually, since too many hence is not good, this leads to this. Okay, following this equation. Okay, so from equation 1. Okay, remember I will often refer to this. Remember this value. Just this important relation. Equation 1 maybe. Okay. Next is what? Hence, according to the problem, initial oxygen before this deoxidation process, what is the oxygen content? 0.037%. That is initial. Initial oxygen content is how much? Is 0.037%. As if you are not happy with this. You are high concentration. You want to lower it, reduce by adding silicon. So final is what? Final requirement is what? Final oxygen content. Any requirement given to you in the problem? See, what is your, how much? Subsequently, this steel is to be deoxidized to a residual 0.015%. This residual 0.015%, that is the final oxygen content. That is desired. So 0.015%. Now you see, I don't think you will need these steps. Can I remove these steps? It's better I go solution of problem 5. Solution of problem 5 is okay. Now we can write. Okay, this. So, what is this? So, if the per ton of steel, how many kg of silicon needs to be added per ton of steel? So, basis is 1 ton, that is 1000 kg of steel. So gives you what is the initial oxygen. So initial oxygen is how much? Initial O is how many kg? 0.037% means 0.037 kg out of 100 kg, but actually there is 1000 kg still, so it is 0.37 kg initial oxygen. And what is the final oxygen? Final oxygen is what? Final oxygen is what? Similarly, 0.015, likewise 0.015% means per 100 kg times 1000 is 0.15 kg. So how much oxygen is removed? So oxygen removed is how many kg? 0.37 minus 0.15 is 0.22 kg. How much silicon is needed for this purpose? To remove this oxygen, consider the stoichiometry. What stoichiometry? Silicon will remove oxygen. Silicon plus 2O is SiO2. Silicon O2 or 2O, whatever, you can write O2 also. O2 means, right here O2 is 2O is equivalent to O2. This is equivalent to 2O, okay. So what is happening? So silicon required to remove 0.22 kg oxygen. I am writing oxygen this way, oxygen. Otherwise, you may consider this as 0. Okay, 0.22 kg oxygen is what? Is how much? Is what? See, this is how much? 28. This is 28. This is 32. So how much silicon? 28 required for 32 kg. And how much is for 0.22 kg? Is what? How much it is? 28 by 32.2 is 0.19 kg. 0.19 kg silicon. You write here once more. Silicon required to remove 0.9 kg is silicon. Okay, silicon. So this is one job. This much silicon must be added for deoxidation purpose to remove this. But this is not enough. Some silicon is retained, find that amount also. So that amount plus this amount will be the total amount. So how much is silicon is retained at equilibrium? So consider the equilibrium. Next, consider the equilibrium. What equilibrium? That this deoxidation. Consider the deoxidation by silicon, right? What is the reaction that you are considering? Deoxidation by silicon. So how you write this? Silicon, and you have to use standard state. You apply this. There should be equilibrium value you will find. Equilibrium. So it is actually a equilibrium constant calculation. Means you need delta G0. Means standard state. And which standard state? Then the question comes, which standard state? Now, convenient is weight percent short, or if you write full, 1 weight percent in liquid iron. Silicon, right here, 1 weight percent in liquid iron, that is Hernian standard state, plus 2 oxygen. Okay, you can underscore if you like, then 2 oxygen. That is also 1 weight percent standard state. Okay, in liquid iron. I'm writing now, but in liquid iron, okay, goes to okay, liquid iron. 1 weight percent I'm writing here. In liquid iron is, what is the product? SiO2, which form? Solid. Note why it is solid. I am removing one by one. This line I will save somewhere. I will save somewhere. Where shall I save? Maybe I will save here. Then I can remove all these things. Okay. Okay. Anyway, let us go ahead. What is this? Silica solid. What is the melting point? Note. Why solid? Why not liquid? Silica. Note melting point of SiO2 is 1723 degrees centigrade. It is above 1600 degrees centigrade. So it will remain as solid. Okay, giving this. So now what is the delta G0? You must know, and you can easily get it from data book. Delta G0 is what? When we write minus this actually I can write, I can give you delta G0 in case it helps you. Acha. You write is delta G0 is how much? This is your question. So for this, I'm just saving this line, this very important line. Sometimes I will use weight percent carbon times weight percent of oxygen is how much? 0.0022. Save this on there. Then you know this all. So you don't need. Now why? Delta G why? But for this I give you more basic data so that you can combine and get this reaction as overall and get the overall delta G0. So what is this silicon weight percent? I am writing in short weight percent. You understand? This weight percent is 1 weight percent in liquid iron plus silicon weight percent plus O2 gas phase. This is O2 gas, not 2O. O2. I am writing. Now this data is SiO2 solid. Delta G0 is how much? Minus 83340. 833,400 plus 229.5 plus 229.5 T joule. Okay, happy. Next is what you need to get here from here O2 to 2O. 2O on the left hand side and O2 on the right hand side. So if you add this, then it will cancel out and give you this as the overall. So O2 on the right hand side, 2O again weight percent means 1 weight percent in liquid iron. Short weight percent 2O goes to O2 gas. Delta G0 is what? How much? 322,600 plus 12.82 T joule. So if you add these two plus then you will see this. You see this cancel. So get leaving here, giving this plus 2O weight percent. See, you are getting here 2 weight percent goes to SiO2 solid, and your desired delta G0 is how much? Minus 610800. 800 plus 242.32 plus 242.32 T joule. Okay, then what you are getting from this? Okay, delta G0, what temperature? You are talking about this. The temperature remains same. Okay, temperature T remains 1600 due to deoxidation process. Temperature has not changed. Okay, so but that is also actually deoxidation is an exothermic reaction. Okay, so but anyway we have considered that the temperature has not changed. So delta G0 what temperature? The same temperature, namely 1873. How much it is? Is it calculated? It is not calculated. Okay, but anyway. Suppose you can calculate yourself, giving you equilibrium constant 1873 through the use of delta G0 is minus R3 ln K. Is what equilibrium constant? This value is 23,811. Okay, do this. This is what you write this expression for this what? Write this. Right here, important, right here. Silica is what phase? Solid. Very important. Remember, this is these are standard states. This is Raoultian. This is Hernian. And delta G0 is the difference. Okay, anyway. So your activities will be reported in terms of respective standard state. So activity of SiO2 with respect to solid standard state, and SiO2 is produced solid. So with respect to solid SiO2 pure solid standard state, activity will be 1. But let us write it A SiO2. Then what you write? HSi times HO square, right? Weight percent. HSi weight percent, HO weight percent Hernian, weight percent standard state. That's it. And this is how much you write nicely. Okay, that it is 1. So initial oxygen and final oxygen. Okay, this is used already. This is already used here. Initial carbon already used. I don't think in case you okay. Let us. I think let us remove this. But anyway, let us see how long we can retain this. Or HSI is what, by the way? HSI. Shall I write this HSI? Again, for approximation, this approximation we make, we consider Hernian activity coefficient is 1, and that is again why the interactions are ignorable, are small. Interaction is what? What is this Hernian activity coefficients? Contains interaction coefficient time corresponding percentage. If percentage are very small, like oxygen, very small, then we can ignoring this, removing this term is justified. Ignoring this term is justified. If this weight percent is small, so we say interaction is small, or directly interaction coefficient is very small. Okay, interaction coefficient is very small. Okay, what is that? Okay, remember 0, 1, nitrogen, E and N is 0, or a very small, say 0.002, like this. So anyway, for approximation at least we can consider this is nothing but weight percent silicon. Right here, right this, right left, right that is. Admit that I am considering this. Okay, otherwise calculate, no problem. Understanding is more important. Putting this APSI number of times you are doing, so you can do this. Okay, don't worry. I will do this. If sometimes I am doing weight percent silicon, and this is also weight percent oxygen squared. Okay. Let us see weight percent silicon is your again in case if you are interested, you write in this equilibrium. Not bad idea. This is the equilibrium relation, and you want to know weight percent silicon in equilibrium. Silicon is deoxidizing, but some held back because of equilibrium property. It will not fully convert. It will not fully convert into SiO2 by removing oxygen. It will remove oxygen. Oxygen may be almost removed, but for this purpose there is the equilibrium, these two. So weight percent silicon, weight percent oxygen is how much? This is also given to you finally. Thank you. I have not removed yet. 0.015. You write this. This is good idea. Square. Shall I write this? Yeah, I am writing once more. That is, I am writing for you. 23811 is 1 under numerator, and weight percent silicon, which is the unknown, times what is this? 0.015 whole square. 0.015 whole square. Okay, what is this? 0.015 whole square. Let me check this. 0.015 whole square. If you find this gives you weight percent silicon. You write this. Which type of weight percent silicon? This is one weight percent silicon. Another is weight percent silicon. You have, okay. So see, weight percent silicon, then weight silicon in mass of silicon, weight percent weight of silicon or mass of silicon. Here one, another already sitting here, waiting silicon, that will weight percent silicon. You write this. Why? Write this. oxygen will be silicon. Oxygen is 0.015. Remember, two stages. First stage is normal steel making. Then what is the blown with oxygen to 0.06% carbon. Then from that you get what? What is the corresponding oxygen? From the relation, this relation is 0.0037 perhaps. Okay. So that you 0.037 actually, this is right, 0.037 oxygen. So see, this is one stage. Now you actually want, for some reason, that further this oxygen is not permissible. 0.037 is not permissible. It should be down to 0.015. How? Deoxidizer. Who? Silicon. What it will do? Silicon plus oxygen. Say oxygen in weight percent liquid steel, or oxygen that is present in the system as gas. Equivalent, because they are striking equilibrium also. They are equivalent. So silicon will react with oxygen in steel. Let us consider oxygen in steel through this reaction and forming SiO, silicon. That will be discarded. So our desired thing is done. But in the process, some silicon will be left behind because of the equilibrium consideration. Equilibrium constant is a silicon. How much? It is not negligible. It is how much? Or weight percent silicon is what type of silicon? You write this. Then it at equilibrium of the deoxidation process. First is steelmaking equilibrium. Carbon oxygen. Carbon corresponding oxygen is together. Carbon oxygen at equilibrium. 1873. Okay, write this. It is at 1873 K and PCO. The exit pressure is approximately CO, exit gas. These two concentrations, and equilibrium. Right? Will you write? Right here, equilibrium relation. So you don't have any trouble. Equilibrium relation, useful, very useful. Quick, you'll see it in Tagdogan's book. Use this. Okay, very quick. Okay, so this is okay. So this is anyway. This is very common, very quick, very fast. So this is one equilibrium, that is steel making. Then this is deoxidation equilibrium. So I am writing weight per silicon at equilibrium means deoxidation equilibrium. If I shall I write deoxidation equilibrium? Okay, equilibrium is right here because silicon comes into picture for deoxidation purpose. So deoxidation equilibrium. Okay, equilibrium or residual. Bapu, come on here. আস্তে আস্তে চলে ফিরিয়ে পড়ে গেছে। This is Solent. I don't know how it is today. পড়ে গেছে। Sorry for the interruption. কি করি? ঢুকে গেছে হাত দিয়ে পাওয়া যাবে না, ফেরো না। না না না, এইটা আসল জিনিসটা কোথায় পড়লো? এটা কো এখানে এখানে লেগে আছে কি? হ্যাঁ, এবারে কোনটা তো কি লঙ্কা কোন দেখে করতে হবে না। দেখো শিখে দেখো ওটা খুলে কেমন আছে দেখতে করতে হবে। হয় না কখন আজকে হলো কেন এটা করে দেখে আমাকে করতে হবে। ওটাকে রাখ এখানে পাশে কম্পেয়ার করে পড়লাম করতে হবে। এটা বাঁ দিকে হ্যাঁ কী করলাম এইটা যাবে সামনের দিকে। ছবি কিছু রয়েছে। স্লাইড করে খুব ইজি ছিল, খুব স্লাইড করে চলে যাচ্ছে। কি করলাম প্রেস করতে হবে না? তখন খেলা করলাম একবার, দেখি তো করে ফেললাম। এদিকে থাকবে, স্লাইড করলো। সেই যখন বেরিয়ে নিয়েছে এই তিনটে, যেহেতু তিনটে এখানে থাকবে, এবার যাবে।
তাই তুমি ওইটা নিয়েই করে নাও না,
কোন নেই,
ওটা নিয়ে হবে না।
খারাপ তো। ইজি একদম, বারবার খুলে করলাম ফলফের পারপাস অ্যাকচুয়ালি, হ্যাঁ। তো আই এম এক্সপার্ট। এই যে আটকিস আছে, আটকিস আছে,
না
আমি করেছি, দুবার করেছি আমি একদম ওই জন্য। আজকে হচ্ছে এরকম করে থাকবে না, নর্মাল স্টেটটা কি এরকম করে আছে।
ওখানে কিছু ভেঙে যায়নি তো, যেখানে তোমার গ্রুভে লাগছে না?
বলছি না দেখুন সোজা একটা আসলে পেয়েছি কথা বলতে দেখতে যেহেতু বারবার হচ্ছে, ওখানে ওখানে দিয়েছিল আরেকবার হয়েছিল, তো এটাই হচ্ছে বারবার, এটা এই দিক দিয়ে ভালো ঠিক আছে। দেখুন দুটো ঠিক আছে, আস্তে করে ডিস্টার্ব করুন। ঠিক আছে, সরি দুটো ঠিকঠাক আছে, অ্যাজ ইট শুড বি normal.
Normal.
Is okay?
Continue.
So sorry for the interruption. Actually, there was a microphone problem, so actually I was held up. Please, sorry, bear with me. So what I was discussing here, equilibrium, or what you can call it, residual, or what you can call it, okay, silicon final equilibrium, or what person silicon final, or what you can write final, okay, equilibrium, okay, equilibrium like yes, or you can say residual, equilibrium, final, residual. And just like residual, good, residual. After deoxidation, how much silicon is what? If you calculate this out, what percent silicon will be, if you calculate this, is 0.187. That is approximately 0.19. Okay, I am removing this line now. Okay. Oh, actually these are also shown here. Fortunate that these are shown here. No problem. Okay, so if this is 0.198% silicon is percent, so what is the kg? How many kg? Kg is 0.19 over 100 times ton means 1 ton means 1000 kg. So it is 1.9 kg silicon. So you have the answer now. So much silicon after deoxidation process, silicon is left, and how much silicon has removed in the form of SiO2? 0.19 kg. So total silicon that you added for the deoxidation purpose is this plus this. So this is the answer. So total silicon, so let us write. So total silicon needed to be added. What is the question? How many kg needs to be added? Total silicon needs to be added is 0.19 kg. Okay, you can underline here 0.19 kg. 0.19 kg. What is the purpose? 19 kg plus 1.9 kg gives you 2.09 kg. Answer. This is the answer. So I may show you here as a breakup. So I'm showing here. Just it may help you to see the breakup. So answer is this, the explanation. This is the answer. 2.09 kg of silicon. How it is utilized? Of which 0.19 kg silicon. 0.19 kg silicon. What is the purpose? 0.19 kg silicon purpose to remove oxygen. To remove oxygen in the form of SiO2. So what is this? To remove removed as So this silicon is removed as SiO2. This is one part, and what is the residual? 1.9 kg, 90 kg silicon. What is this? This is the residual or remaining in steel. This is remaining even after the deoxidation process. This is remaining in steel. So remaining or residual, remaining in steel. So this is your answer. This is also answer. This is the answer. This is the explanation, further explanation. So problem 5 is over. So we will take up now problem 6. Problem 6 is already written. So let me remove this problem 5. Let us see if I can. Oh. Sorry. Problem 5 over. I want to remove this. Maybe I will use this space for solving the subsequent problems. Okay, very good. That's it. Solution of problem 6. Better I keep this space empty now. Maybe when I will actually refer, okay, to the top part, okay, then I will use this space. So I remove this answer. So I remove everything here. Everything here. Solution problem 6. So this is the problem. It is already written, so let us read this problem. A heat of steel is made in the normal manner in a basic oxygen furnace. At tap T is 1850 Kelvin, slightly short of 1873. Okay, 1850 Kelvin, and carbon is 0.6%. This is at tap. Okay, immediately after tap, magnesium is injected into the liquid steel. Now, magnesium is also a deoxidizer. But magnesium injected, but question is, this time, is there any tendency for the magnesium to react with oxygen in steel? Tendency means thermodynamic tendency means delta T is negative or not. For magnesium and the oxygen that is present in the steel. Oxygen, you can consider oxygen percentage as a dissolved oxygen in steel or oxygen gas. Okay, but the corresponding value of oxygen gas. Okay, the oxygen gas may be useful here. Let us see. You can do this. Okay, so first of all, you see this equilibrium, consider the equilibrium. Okay, to find the PO2 in the exit gas. We know it is very small. We know it is actually mainly CO gas. So, but let us find out, and then we will see whether magnesium with this partial pressure of oxygen will react to form magnesium oxide. Okay, like this. Okay, so magnesium oxide solid, because at this temperature magnesium oxide is actually high melting, so solid. So to find the PO2 in the exit gas, how do you get this? So consider the equilibrium. What you can consider the equilibrium, that is the exit gas at tap. When it is tapped, actually 0 versus oxygen. So consider the equilibrium. What equilibrium you consider? Carbon weight percent plus, you see, two ways you can do this. Oxygen weight percent, this CO gas, this already you know, this value you know. If PCO is 1 atmosphere, you know. PCO is 1 atmosphere given. So you know this is the relationship, okay? But weight percent oxygen you don't want, you actually have data or magnesium, which is liquid actually at this temperature, plus oxygen gas is magnesium oxide solid, the product which is refractory and high melting and solid. So for this oxygen gas is needed. So you prefer here not necessarily oxygen weight percent always. Suppose you want oxygen gas, it is given to you. Actually, yes, it is oxygen gas will be preferred species, and then half O2 obviously half O2 is CO gas, and delta G0 you take it from me, okay, it is no problem. This is what, minus 136984 minus 43.51 T. You want to see the equilibrium PO2 gas. I tell you, explaining. Here you will get PO2 equilibrium. Here you will get weight percent oxygen at equilibrium. Repeat, PO2 equilibrium versus weight percent equilibrium. Okay. So PO2 you will get here. Let me find out PO2 equilibrium. Then I will show you the actual inner meaning of this or interrelationship. You have choice of considering oxygen gas or weight percent because they are interrelated. They are also striking an equilibrium. Oxygen gas, why you have weight percent oxygen in steel? Why oxygen in steel? Because oxygen gas is there. Small maybe. So that's why weight percent oxygen are also small. And that small value is very big problem. That we know. So we want to make the small value smaller. Small oxygen smaller, small nitrogen smaller, still smaller. Sulfur still smaller. So the oxidation. So here these are equivalent. These and these equivalent because they are also in equilibrium. So they have their equilibrium relationship. So any will do. Let me find out PO2 gas, and then I will show you what is the what if we consider this, or what is the difference between considering this equilibrium plus C plus what equilibrium you consider this last time, C plus C weight percent plus oxygen weight percent goes to CO gas. So try to actually remove any mental block, okay? Concept, clarify your concept, okay? And Joule, this is Joule, okay? Let us consider delta G0. So you get delta G0, what temperature? This problem is 1850 Kelvin. 1850 Kelvin is how much is it? Is actually, I'll tell you what is. You find out yourself and then get equilibrium constant 1850. This I have calculated 1850, or this I have saved actually this value 1382567. 1382567 is what? What is the equilibrium constant expression? You tell me. Is what? Write nicely. PCO numerator, HC weight percent, because it is Hernian standard state. This is again gas means Gaussian, means PO2. And again, if you are very meticulous, you can give this here equilibrium. Okay, if you don't want it, to avoid any confusion, give this, or it is implied. Good boy. So PCO is what? What is the PCO? Okay, gas. That is gas. See, PCO is 1. PO2 the unknown. What is the HC? Again here you do this consideration. HC is weight percent carbon. Means Hernian activity coefficient is 1. So is approximately with some approximation and admitting some or admitting little error, a small error, okay, maybe incurring small error or negligible error, maybe 8% carbon. Okay, if you want to be meticulous or very scrupulous about this, okay, then you can consider FC, Hernian activity coefficient, FC 8% carbon, and FC is what? Log FC is ECC 8% carbon, etc. This I am doing and will be doing again, but let us solve this problem with this approximation. What is this? This 8% carbon is how much? Is given to you 0.6%. 0.6 or PO2 equilibrium or PO2 equilibrium is what? Sorry. Actually, very good. Actually, I consider FC. Actually, I consider. Okay, sir. FC. Tell me FC. FC times. Tell me FC. 8% carbon. FC is what? FC is what? Okay. FC what? No. Okay. FC is actually FC 8% carbon. No, sorry. This I have not got that consideration. Sorry, I made this is approximately 8% carbon. What I wrote at the beginning is correct. And what is this value? This is again what? 0.6%. 0.6. So what you are getting out of this? PO2 equilibrium unknown. I'm sorry, unnecessary, because you have to log FC. You have to find it from ECC. Okay, and okay, no problem. Maybe it will be close to 1. So you consider it or not, you will have the same value. Okay, good, very good. What is this? PO2 is how much? 1.45 times 10 to the minus 14 atmosphere. So PO2 equilibrium. Now magnesium is added to the liquid still. Okay, added to liquid still, and magnesium may react with this depending upon its equilibrium value and this value. The equilibrium value for magnesium oxide system, and this is a PO2 in the steel. This is again always oxygen potential comparison. then we will decide whether the reaction under study, namely magnesium plus oxygen goes to magnesium oxide, will occur or not. So consider this equilibrium. Next one, okay. So next consider. Let us now find PO2 equilibrium with which system? MgO. I am writing for you Mg liquid, MgO solid. MgO liquid, I tell you, magnesium, say magnesium chips are added, okay, magnesium ribbon added, pieces of magnesium added, that low melting magnesium, 650 degree or like this, and this will be liquid. And magnesium and iron, magnesium doesn't have much solubility in iron, so we will consider magnesium is pure. So pure liquid magnesium, pure and MgO is solid. Okay, then what is the PO2 equilibrium? So for this, let us consider this equilibrium. Okay. So one thing I tell you before I tell you here, I found this, but weight percent oxygen you will find how weight percent oxygen. If I ask you what is the weight percent oxygen, you would say carbon concentration is how much? 0.6. 0.6 times weight percent oxygen is 0.0022. Okay. So this is in passing. This is in passing. In passing, I will show you in passing note. Weight percent oxygen is what? Weight percent oxygen is what? Tell me. 0.0022 over weight percent carbon. Weight percent carbon, which is like this, 0.6. So weight percent, okay, like this, okay, it will be about 0.4 or 0.04 maybe, close to 0.04. So say close, okay, 0.037, okay, 0.037. Anyway, this point 0.04, 0.00, no, how much it is? How many? 4, 1, 2, 3, 4. 0.00, no, this is actually, this will be divided by 0.6, it is 0.6. Weight carbon is 0.6, okay, just 0.00, roughly 4. It's okay. So this oxygen, weight percent oxygen, and this PO2 are equivalent. This weight percent oxygen, this weight percent oxygen and PO2 equilibrium of how much? Of what value? 1.45 times 10 to the minus 14 atmosphere are equivalent. Equivalent or in equilibrium, or in equilibrium. That's why equivalent or in equilibrium. How do you know this? Because you may strike equilibrium like this. Half O2 gas goes to oxygen weight percent. So if you, and this is equilibrium, you get equilibrium constant. Equilibrium, right here, equilibrium. Consider this equilibrium. This is also equilibrium. See, this is in equilibrium. This is what? Carbon, weight percent carbon times, okay, this is what equilibrium this is? Yeah, this is what? I'll show you. What is this equilibrium? This is carbon weight percent plus oxygen weight percent. Is CO gas. This is almost same, only half O2 gas is replaced by oxygen weight percent. It is also this equilibrium or this equilibrium. What is the difference? This here and this there. These are again in equilibrium. So that's why you can write anything, any of these two. You can write in this form or this form, along with these two. So as I say, and I showed you here. This equilibrium holds. That's why any you can write. And how to find this? Okay, that these are equivalent. K is what? HO by PO2 power half. K is known. K is a known quantity from delta G0. Delta G0 is known. K is known. HO is nothing but weight percent oxygen. Weight percent oxygen by PO2 power half. So what is this value? If PO2 is this value, substitute weight percent oxygen will be what value? Any will do. But then why we prefer oxygen gas? Because for the one that I am going to write this for magnesium, say oxygen gas data available. Magnesium plus oxygen gas is MgO. So PO2 equilibrium. Then they add PO2 equilibrium and the PO2 that you have calculated here, compare, and we will decide whether magnesium will oxidize oxygen gas in the furnace, in the converter, will oxidize oxygen. Will react with oxygen or not? That will be seen. Okay, that will be found. So let us remove this unnecessary, just digression. Okay, but I wanted to clarify these points. These are actually equivalent. Always remember these. These are equivalent. They strike equilibrium. Oxygen gas and oxygen weight percent. Oxygen weight percent in steel, in liquid iron, liquid steel, and oxygen gas in the gas form, in the exit gas, which is in equilibrium with the two other phases, slag and metal. These three phases are in equilibrium. We consider this. Okay. So you can apply any with any. So gas and oxygen. We choose oxygen and oxygen gas, the pertinent one. And equilibrium. This equilibrium is okay. This is also the equilibrium. Oxygen gas. Now you say oxygen gas is very small. You say negligible. Yes, negligible. Still I say negligible. Because oxygen weight percent is also negligible. But this negligible wreaks havoc. Very serious. Low value is very, even though low, small, minor, very important. So, to certain extent of this value, okay, this small maybe, but that may be very harmful for steel property. So I remove this, remove this. So remember, so let us consider our study. Mg plus, so get the delta G0 properly right. So magnesium solid, I will show you here, plus half O2 gas, MgO solid. Delta G0 is how much? Delta G0 minus 600, 950. 950 plus 107.57 T plus 107.57 T joule. 57 T joule. Okay. Then another one is what? Magnesium liquid goes to magnesium solid. Very simple, very simple. This is what delta G0 is what? Minus 8954 plus 9.71 T joule. If we add these two, again plus, you have magnesium solid. Cancel out, okay, what remains? Magnesium liquid plus half O2 gas goes to MgO solid, and what is the resulting delta G0 is what? Minus 609904, minus 609904 plus 107.28 117.28 T joule, 28 T joule. What is this? Get delta. Remember, when you add magnesium, follow magnesium solid, you are adding that, and it is becoming liquid. And in the liquid phase, and in the liquid state, but it doesn't dissolve in iron because it is immiscible, negligible, or nothing can be totally insoluble, but negligible. So almost pure liquid Mg, reacting with oxygen gas, small though whatever, in the system and forming MgO solid. This is what we're trying to see whether this is possible. Okay, the proposed reaction, this is the reaction under study. Okay, this is an MgO solid. Why? Because its melting point is actually, MgO is actually high melting. It is about 2600 or such value, high values, degree centigrade. So it is 1600 degree centigrade or thereabout. Okay, 1950, 1850 Kelvin, close to 1600. So this is remain solid. So this is the okay. Or get delta G0. What temperature? The temperature is actually okay. This temperature is not going to change for this magnesium addition. Is how much? Is not given again. I'm not about if you get this gives you K equilibrium constant 1850 from delta G0. Delta G0 is minus, or Steelmkng note delta G0. You know this, but I am writing once more from this. And article K is how much coming? K 1.24 times 10 to the power 11. And write the expression for equilibrium constant. Again write C AMGO solid, actually MgO solid, AMGO solid. So write this AMG liquid, PO2 power half. This is how much? Pure MgO solid. Okay, so it doesn't mix up with anything. Okay, it doesn't go into the slag phase redox consider. So this is an Mg liquid. So since it is essentially not soluble in iron, liquid iron. So Mg is insoluble in liquid iron. You may consider this. Mg is 1 because Mg does not dissolve in liquid iron. Because Mg, so liquid, so it may form an alloy with iron, but because Mg does not dissolve in the liquid metal phase in liquid iron. That's it. So that's why almost 1. This 1. So what you get out of the, give a star mark here. So dissolve in liquid iron. Let me write here. Dissolve in liquid iron. Right here. Then give a star here. Star here. Where I will give this part is removable. You remove this. Solution of what are right? Okay, sorry. Problem 5 already over. Solution problem 6 we are running. So PO2 equilibrium. See equilibrium number of times we said. PO2 equilibrium. This I said in Hernian diagram discussion. The PO2 of AAO2 system and PO2 equilibrium of AAO2 system. A plus O2 is AO2. And BBO system, PO2 equilibrium, BBO system. B plus half O2 is BO. This I said, this example. Then I said both are equilibrium, but for one system, it has own equilibrium, and what is the actual? The equilibrium of the other serves as the actual value, Q. Q less than K, or 1 by Q, greater than 1 by K, leading to delta G is negative, the second law of thermodynamics. One's equilibrium acts as the actual for the other, for its counterpart, for its contender. for its rival. Here who are the rival? Magnesium manganese oxide system is one. It has an equilibrium value. And another purity equilibrium here in the steel, having the equilibrium of this equilibrium. This equilibrium, carbon, carbon in liquid iron plus half O2 gas, steel, okay, carbon in liquid, okay, steel plus half O2 gas is CO gas, this equilibrium. C plus half O2 is CO is also Lilium line. Then here standard state is, the concept is, standard state is actual white person standard state. Okay, there we consider all pure Raoulsian standard state. So anyway, so this is one purity equilibrium, this is another purity equilibrium. Well, I wrote, oh, I have not written yet, I thought I had. Purity equilibrium, let's calculate this. Purity equilibrium is what? Purity equilibrium, which system, right, specify? Magnesium, solid, liquid, I am very sorry, and magnesium oxide solid, whichever it is how much value is, if you calculate this, others are known, it is actually 3 times 6.45 times 10 to the power minus 23. Imagine which level we are talking. Oxygen, one pressure is 10 to the power minus 14 atmosphere. CO gas is, why it is not 1? Right? It should be 1. What is its contribution to the total? But how serious is this value? This value and this value will be compared and will decide whether magnesium has any tendency to react with oxygen present in steel. And if it has tendency, then magnesium will remove oxygen, deoxidize steel, which you want. So, but the question is only whether tendency means delta G negative or not. So, you know, Q less than K, remember all those things? Since now, what is the meaning? Just recall. What is the meaning of this value? When magnesium will oxidize, react with oxygen to form MgO solid, when the reaction will move in this direction, when PO2 existing in the system, actually present in the system, existing in the system is greater than its equilibrium value, which is 10 to the power minus 23 atmosphere. Any value greater than this will cause, it present, this will cause magnesium liquid to react with oxygen. Any value present. So since what is present in the liquid steel system, okay, in this BOF system, non-BOF system is what is this? This is greater than this. Any value greater than this will cause oxidation of magnesium. Repeat. Any value, this says what? Any value greater than this will cause oxidation of magnesium. According to this relation. Follow this way. And why? Because delta G will be negative. Delta G will be negative. Or if you consider delta S universe, that will be positive. Delta G will be negative. Okay? So because or say Q less than K or 1 by Q greater than 1 by K. This is it. Here it is actually coming on the 1 by side. 1 by Q greater than 1 by K. So it is greater than this. So since this is any value greater than will cause magnesium oxidation. Magnesium oxidation means magnesium will remove oxygen from its surroundings. Means here liquid steel added surrounding. So since 1.45, I am writing PO2. 1.45 times 10 to the minus 14. What is this? PO2. Where present? CO. CO 8%, right? In normally CCO means C graphite standard state. Okay. CO 8% means 108% liquid iron. Okay. CCO. You understand that? This is PO2 this is I will write here is greater than what is this 6.45 times 10 to the minus 23 atmosphere. Oh, sorry, sir. Atmosphere. What is this, sir? mg, right? I'm sorry, write this way is is PO2 mg solid. Write nicely mg. I am very sorry. mg liquid. mg liquid. Magnesium is a low melting metal and MgO is a high melting ceramic solid. So the competition. These two are contenders. Okay, this is a tug of war between these. Who will oxidize whom? If the reverse occurred, CO will oxidize. Yeah, okay. Magnesium will actually react with oxygen. CO, in that case, magnesium will react with oxygen, forming MgO. MgO, the reverse it happened. Okay, MgO will be dissociated back into Mg plus oxygen. Like MgO plus carbon will give you Mg plus. Okay, this it will dissociate back into this. Okay, sorry. Okay, the reverse would occur. Okay, greater than. So what will happen? Since this, we write this. Since this magnesium liquid will have tendency to react with oxygen. Which oxygen is surrounding? Surrounding is steel. It has oxygen. To react with oxygen in steel. Right. If the reverse occurred, then what would happen? C will react with reduced MgO. She will reduce MgO, forming Mg liquid and CO gas in the reverse case. But you know how difficult it is called carbothermic reduction of MgO. Okay, all these things. Okay, so difficult, so impossible. See, this is the possible thing to have a tendency answer. Let us proceed. We took much time, and also there was interruption in our microphone. So I'm sorry. So let us take up next problems. Problem 7. Let us take up and remove these also. Problem 6. Remove this. Problem 6. Problem 6, remove this. Problem 7. Solution of problem 7. So draw a line here. Solution. Problem 7. What is this? A steel made conventionally in a basic oxygen furnace is tapped out at 0.067% carbon. This is the carbon equilibrium value, weight percent carbon at equilibrium, and at tap we consider equilibrium prevails, equilibrium occurs. So 0.067%, immediately you know weight percent oxygen through this famous relation. One you know the other. At equilibrium, very good. You know what is the weight percent oxygen, very good information. So very useful information. Anyway, I don't know what is asked. Let us read on. Oh, it is vacuum carbon deoxidized by lowering the pressure over a stirred ladle. Take a ladle, stirred ladle of the steel. It took the steel that is produced in BOF in a ladle and then subject to vacuum. Okay, and the process is vacuum carbon deoxidation. Okay, we have actually 3 standard methods. Okay, this I may write here just for your information. One is vacuum BOD. What is BOD? This is not exactly BOD. It is written on. It is vacuum. You know this? Oxygen decarbonization. Carbon removal, very important in steel. We want actually strain is low carbon steel. So vacuum oxygen, like say 0.02 to 0.2 maximum, so very low carbon. Vacuum oxygen decarbonization. Decarbonization. This is BOD. There is another is AOD. This is not vacuum, but argon in principle does the same thing. You reduce the it helps to decarbonize, to produce CO gas, by lowering the pressure of the product gas. So argon, here vacuum reduces the pressure, here presence of argon dilutes the pressure, reduces the partial pressure of CO gas. So argon, oxygen, decarbonization. Again, same. And another is vacuum, vacuum arc degassing. So you see here vacuum is used in 2 cases and argon is in the 3rd case, and argon will take up this process, argon oxygen. But they say not vacuum oxygen decarbonization, the vacuum carbon deoxidation. Vacuum carbon deoxidation. So this is actually here aim is to remove oxygen. Here the aim to reduce the oxygen. Remove oxygen, no doubt, to remove oxygen or say to reduce the oxygen concentration. Vacuum carbon deoxidization. This was what? Vacuum oxygen decarbonization. So our aim was minimize carbon, or reduce carbon content, This was this, decrease the carbon content. So anyway, this is the let us read out. It is vacuum carbon deoxidized by lowering. This is already said. By lowering the pressure over a stirred ladle. So steel produced in the BOF taken in a ladle and subjected to vacuum steel. The vacuum system removed 450 STP liters of CO, standard temperature and pressure, STP. You know, S is standard temperature 0 degree centigrade, pressure is 1 atmosphere. So of CO per ton of steel. Temperature is 1873 Kelvin. Calculate the carbon and oxygen contents of the steel after the deoxidation process. After the deoxidation, this carbon is given here. No, this is a tap in the furnace. In the converter, basic oxygen furnace. So this is carbon. So, but it is after this vacuum carbon deoxidation process. What is the equilibrium value of carbon and oxygen? Calculate, and finally also calculate the equilibrium PCO corresponding to this carbon and oxygen, which is actually you have to strike a equilibrium with CO gas, carbon and oxygen, very easy. But first part you try to solve problem 7. So let me sketch this problem maybe. I can sketch this problem for you. So not bad. This is the ladle. Consider the ladle part. This is the ladle. We have taken only this. There is no question of any slag as a liquid metal. Okay. What it is there? Iron, obviously carbon and oxygen, metal, liquid metal. Metal. What you are doing? You are subjecting it to vacuum. Vacuum. What is said about vacuum? This okay, vacuum. Question is what is this? Anything else? Okay, no. P vacuum is PCO. You write here P vacuum is PCO. This last part PCO is how much? This part. This is the last part. But before this important part is more important, I would say rather, that carbon and oxygen. Unless you find the carbon content and oxygen content, you cannot find this part. Okay. So concentrate on carbon and oxygen content after 450 cc of CO gas. Okay. What is removed here? CO gas. Vacuum is extracting, withdrawing CO gas from the system. By the reaction of carbon plus oxygen, it is promoting the reaction of C plus O goes to CO. Let us write this out. Okay. So this tap carbon percentage is how much? Tap is what is given here? 0.067. 0.067%. Okay, very good. Tap of oxygen percent is what? Is what? So this is what you write this 0.0022 over 0.067 gives you what value? 0.033. 0.033%. So what is this equivalent to? In 1 ton, basis is what? Per ton of steel. I'll come to this CO gas. Basis 1 ton means 1000 kg of steel. So tell me what is how many kg? Oxygen percentage 0.00033. How many kg of oxygen is nothing but per 100 kg 0.033 kg. So 0.033 kg per 100 kg per ton means 1000 kg is how much it is? 0.33 kg oxygen. O. Oxygen you can write this kg O. Similarly, will you write this one? Okay, kg O. This is very good. What is this? What is how many kg here? Equivalent to how many kg? 0.067 by 100 times 1000. Remove this VOD, VAD, yes, this is all over. You know this perhaps is 0.67 kg carbon. This is understanding. Okay. Now what has happened? This has vacuum has removed carbon and oxygen both in the form of CO, promoting the reaction C plus O goes to CO. Let us write this out. So first of all write 450 now. 450 liter STP is equivalent to how many moles? How many moles? PV is nRT. N is PV by RT. Is how many? 1 atmosphere. What is the volume? 450 liter. What is the R? 0.082 liter atmosphere. Temperature is, standard temperature is 0 degree centigrade, means 273. If you do this calculation, this Kelvin, this is liter atmosphere per Kelvin, okay, per mole. This is actually per mole, and this will come as mole, okay. This mole will come to the, so is how much it is? It is about 20.1 mole. 21 mole CO. CO is removed. 456 liter means 21 mole of CO has been withdrawn from this. Okay, okay, very good, very good. 21 mole CO. Or quickly, alternatively, actually I'm writing here. Actually, alternatively I'm writing here, this side, because this is so insignificant. Alternatively, what is this? 22.4 liter, 1 gram mole, 1 mole or 1 gram mole. So 450 divided by 22.4 liter. This is standard value, you know, at STP. 1 gram mole occupies 22.4 liter. Is actually you get the same result. It's 20.1 mole. Same result. Okay, but this is okay. Detailing of the terms. Okay, very good, very good. This is what now you see. Follow this: carbon plus oxygen goes to CO. Carbon weight percent. Carbon in steel means okay, weight percent plus oxygen weight percent is CO gas. So 21.1 mole CO. So 21.1 mole CO is removed. Means 20 point stoichiometry. Okay, it is better you write this stoichiometry. It says 21 mole carbon removed. That is equals to what? 20.1 mole. 1 gram mole is 12 gram. 12 gram times 10 to the minus 3 kg carbon. Okay, yes, kg carbon. Okay, very good. Yes, right, kg carbon. Repeat 20. See, 1 stoichiometry. 1 mole CO removes 1 mole carbon. Okay, your weight percent is a standard, so don't worry. Okay, just remove this. C plus, remove this in case of difficulty. Just underscore. Or simple C plus O is CO. 1 mole CO removed. Removal of 1 mole of CO accompanies removal of 1 mole of CO accompanies removal of 1 mole carbon and 1 mole oxygen. So that I am writing. 21.1 mole CO means carbon removed, and so many mole means 1 gram mole of carbon is 12 gram times 10 to the minus 3 kg carbon. And similarly write 20.1 mole oxygen removed means 20.1 times 16 times 10 to the minus 3. Oh, I should have written here, no? How much kg? This is how much? This is how much? This is right. 0.24 kg carbon. Right? 0.24 kg carbon. Okay. Acha. Is 24 kg carbon. And here it is right. But how many kg? It is point. Kg carbon, it is 0.32. Obviously, 0.32 kg oxygen. Okay. Remove means, okay, is kg carbon removed. Removed, right. Removed, kg oxygen removed. Okay, very good. So remaining carbon and remaining oxygen, what is the concentration? You have to find the percentage of carbon and oxygen. So many kgs removed. How many kgs were present initially before this vacuum treatment? These are the answers for the first answer for carbon and oxygen here. 0.67 kg of carbon, 0.33 kg of oxygen. Let us find out. So remaining, hence remaining carbon is, tell me what was the starting carbon? 0.67 kg. 0.67 minus how many kgs is removed? 0.24 for vacuum treatment is 0.43 kg carbon. In 1 ton of steel, so many kg. 1 ton means 1000 kg. And then what is the percentage carbon? When the carbon content means percentage carbon. So do this. So many kg carbon, 1 ton of steel. So 0.43 kg, 1 ton means 1000 kg. Percentage means 100 kg. Sorry, 100 kg. Remove this. I don't need this. So it is 0.043% carbon. Remaining carbon is 0.043 carbon. After this vacuum carbon deoxidation, what is the remaining? And remaining oxygen similarly is what? What is the starting oxygen? Means at tap 0.33 kg. 0.33 minus how much remove? 0.32. So very close. Is 0.01 kg oxygen. Is how much it is? 0.0 kg oxygen is what? In 1 ton, 0.01 ton means 1000 kg. In 100 kg times 100, it is 0.001% oxygen. This is the answer, first part. I am writing once more. This is the calculate the carbon and oxygen content of the steel after the deoxidation process. You can call it deoxidation, you can call it decarbonization. Both are reduced. Okay? See why both reduce. See, always see like this. This is follow. This remove to produce this, and this exists in the vacuum system to the outside. Through the vacuum system, the outside. Lost. Which you want. So this is the answer. So answers once more. Shall I write? Can you remove this? Yeah, I remove first 2 lines. So answers, I am writing answer. First part. First part is what? Answer. You write this. Percentage carbon is right 0.043%. Percentage oxygen after deoxidation. Answer. First part after deoxidation. It is already given, okay? It is already asked. First part means after deoxidation. After deoxidation of the deoxidation process, okay? After deoxidation. Percent oxygen is what? Answer 0.001%. Second part, remove this. That's another line. Second part, this is first part. Second part. What is the question here? Calculate the equilibrium PCO for the steel after the process. Calculate the equilibrium PCO for the steel. Equilibrium PCO. See where there is C, and I remove this. I'm writing once more. Where there is C and where there is O, C plus O is CO. What is the equilibrium CO? You can easily find out. And that was the deciding factor as to how much vacuum you want to apply. Very interesting. So second part is what? Right, consider the equilibrium. This I often say carbon weight percent, Hernian standard state, etc. I am not writing. 1 weight percent in liquid iron, carbon plus oxygen likewise weight percent goes to CO gas. Okay. What is the equilibrium constant? Tell me. Or you know the answer. Oh, what temperature it is? Oh, temperature I forgot to write. Write the temperature is what temperature? 1873 Kelvin. You have written here. 1873 Kelvin. Same as the steel making temperature. So this equilibrium in the ladle. Okay, 1873. What is your answer? Our answer is what? Here, weight percent carbon. We have standard values. We have standard relation, standard equilibrium relation. Weight percent carbon times weight percent oxygen is 0.0022. Oh, I'm very sorry. Equilibrium constant. Okay, what value remember? Anyone remembering? What value, from which value we got this? 1 by, okay, K equilibrium constant is what? K 1873 is how much? Okay, remember? 451. 451 inverse. If it is 1, then this two product is inverse of 451. And you get inverse of 451 is this value. Rather inverse of this is 451. You get this, okay? But why I said I was sorry? Because PCO is not 1 this time. PCO is find it out. This is for PCO is 1 atmosphere given. So don't use 0.022, but the equilibrium constant is 451. Okay, how you got this? I am showing you. How you got this? See, got this is PCO by weight percent carbon, weight percent oxygen. So when it is 1, then this product will be 1 by 451, which is this. This was our genesis of this. This is how we got this. So remove this. You know, this time PCO is not 1, it's unknown quantity. So write as PCO. Calculate the equilibrium PCO for this still after the process. Okay, so PCO that equilibrium. When equilibrium is attained, the process is there. Okay, that's the end of the process. So PCO after the PCO over, right, weight percent, right, HCO first, right, first HCO weight percent to be formal. HO weight percent, then of course you write, remove this. This is what? PCO approximately HC is weight percent C times this is also weight percent oxygen, right? HI is weight percent, assuming, considering. In fact, here you have considered. Already you have considered. Considering HI is weight percent I. Good boy. Oh, good. So weight percent carbon is substitute now. Again you can write this equilibrium. Always. Here you can write equilibrium. Substitute what is the weight percent carbon? What is weight percent carbon? Oh, answer is where? 0.043. 0.043. And what is the oxygen? 0.001. Let me check if this I am correct or not. Okay. 0.0043, 0.001. Oh, sorry. 0.001. Then you get what? Then this gives you what? PCO, the only unknown is how much? 0.02 This your equilibrium, so write this 0.02 atmosphere. 0.02 atmosphere. Answer. First of all, answer to second part. Bapu, time, can you tell me?
1 hour 51 minutes gone.
Okay, so we'll exact we'll finish at exact time. That is
2 hours means 9 minutes
9
more.
10 minutes maximum. Huh? So thank you. So this is, but this is some comments about this. Why sir? This is us. This is the vacuum requirement. This is the vacuum requirement. What vacuum pressure you will use? 0.02. This is because CO is the only gas. CO is the gas, only gas that will come out. So yes, for this lateral treatment, CO. So why? No. This is the vacuum requirement. Vacuum requirement. Is a question. P vacuum is PCO. What is the vacuum pressure? What is the vacuum pressure? Is PCO. PCO equilibrium actually. PCO equilibrium is how much? Answer is 0.02 atmosphere. Now actually it should be not exact. Since this is in equilibrium, you want to disrupt the equilibrium. Yeah. Make it delta G negative. The equilibrium is delta G 0. To make it negative, actually you will apply. Actually, we will apply P vacuum less than 0.02 atmosphere. Any value less than, this is a critical value. Just any value less than. Means above this you cannot. Above this delta G is, I repeat, previous studies, 0.02 exactly, 0.02 delta G is 0. Equilibrium. Less than this, delta G is negative. Means spontaneously carbon and oxygen will be removed. Now you might say, sir, can we remove further? Yes, if you remove further, then it will be more than 450 STP CO. More 500 liters CO STP. 600, more and more it will be less and less. So what is the what I was talking about this? So repeat. So this refers to delta G is 0, and this refers to delta G is negative. Means okay, this process is will spontaneously occur, and greater than this delta G is positive. Now this vacuum treatment will not work. Thank you. Okay. So shall I write this, or do I have to? Note, additional note. This I discussed. You remember dissociation of magnesium. Assignment 7. There were some problems. That's actually example problems. This I said. Then we discussed assignment 7. So in the example problem, one problem was what vacuum we should use to dissociate MgO solid into Mg vapor and oxygen. So same here. Okay. Additional note. PCO, very interesting. PCO equilibrium. PCO equilibrium is 0.02 signifies delta G is 0. The second law, all in second law. PCO equilibrium less atmosphere 0.02 atmosphere signifies delta G is negative, spontaneous, which is required, and PCO equilibrium greater than 0.02 atmosphere signifies delta G is positive, means impossible. the gas will not be able to come out because pressure is external pressure is greater than equilibrium. So it is suppressing. It is not allowed. And when it is less than equilibrium, it is spontaneously come out. Thank you very much. With this, okay, this problem 7 is out over. Problem 8, I will let me write down the problem 8 and I will take up in the next class. Okay, problem 8 and problem 9. 2 more problems still remaining. So, problem 8, I still maintain this. How much time?
1 hour 56 minutes.
4 minutes. Okay, let me write this problem at least. This will help us save time next class. Problem 8. Problem 8. Let us go slow. A BOF shop. It will 2 minutes. BOF shop uses an argon oxygen mixture. Uses an argon oxygen mixture to attain low oxygen contents. Low oxygen, again see kind of deoxidation. Low oxygen contents of steel when blowing down to a tap content, when blowing down to a tap content of to a flat tap, when the steel is tapped, when a tap content of when a tap going down to a tap carbon content of 0.10% carbon. What should be the what should be the percentage oxygen in the what should be the percentage oxygen in the inlet argon oxygen mixture if 0.01% oxygen is specified as the tap oxygen content. P total 1.3 atmosphere and tap T and tap temperature T is 1873 Kelvin. Reference, same reference, A.E. Morris. And as usual, to check this. I am almost sure, but not 100% sure. So to check. Thank you very much. With this, thank you. We have solved actually 3 problems and started the 4th problem. But we will take up this in the next class, finish this problem and the last problem, problem 9. After this, we will consider free energy versus composition and activity versus composition diagram. Thank you very much. See you in the next class. Bye.